Hello class, let's look at section 5.6 part 2, and this will be the last part of section 5.6 dealing with linear programming. So you did see this in algebra 2. Let's just take a look at one and a half example problems, and just to refresh your memory, how to do linear programming again and what exactly it is. So linear programming is used to find an optimum value. So for example, we could do minimum cost or maximum profit. So this is calculus. In calculus, it's called optimization, but we're trying to find that optimal amount. To solve a linear program problem, there are some steps, though, that you need to follow. All right, so first thing, write all necessary constraints. So these would be our inequalities and the objective function, and that's what we're trying to maximize or minimize. Graph the region of feasible solutions. So this is going to be that shading piece. Identify all vertices. So after we've done our shading, we're going to look at the corners of our shaded area. So any corner is a vertice. Find the value of the objective function at each vertex. So the optimal value is going to occur at a vertex. So we need to put every single vertex point into our objective function and figure out what is the largest if we're trying to maximize or what's the smallest if we're trying to minimize. All right, and then step 5, the solution is given by the vertex producing that optimum value. Okay, so again, if it's the max or the min, depending on what numbers we get, that's going to be our optimal value. Okay, so let's take a look at one example here. So these are going to be word problems that have a lot of information thrown at you. So just start taking out little pieces of information at a time so that you don't get overwhelmed with the amount of information that's being thrown at you, because right away they're going to give you a whole big setup. All right, so this one, earthquake victims in China need medical supplies and bottled water. Each medical kit measures 1 foot cubed and weighs 10 pounds. Each container of water is also 1 foot cubed and weighs 20 pounds. The plane can carry 80,000 pounds with a total volume of 6,000 feet cubed or cubic feet. Each medical kit will aid 6 people. Each container of water will serve 10 people. So there's a whole lot going on in here, a lot of numbers, a lot of different things going on. Ultimately, we're trying to figure out how many of each, so this each is a key word here, should be sent in order to maximize, so we're trying to find the maximum value, the number of victims aided. All right, number for each, and then also then what is this maximum number of victims? So the first thing, when it says how many of each, those are our variables. So the each that we're working with are medical supplies and bottled water. Those are the two variables that we are working with. So let's say X is the medical kits, and let's identify Y as the containers of water, bottled water. We'll just label it as water. So those, when it says how many of each, we're trying to figure out how many medical kits, how many um, kits of bottled water are we going to be able to get onto the plane when it carries 80,000 pounds in the volume. Okay, so that's the first step. Identify what your variables are. What are you working with? Okay, so same setup, but just smaller. Okay, so step 1, constraints and the objective function. So again, X was going to represent our medical kits, and then Y is going to represent containers of water, bottled water. All right, well, we know these are tangible items, so I can say, well, X has to be greater than 0, and Y has to be greater than 0. I can't deal with negative values of medical kits or negative values of water. All right, now let's talk about how much weight we can work with. So it says the plane can carry 80,000 pounds. Okay, so I know 80,000 pounds is going to be the maximum amount my plane can carry. So I'm going to create some function that's going to come out to be less than or equal to 80,000 pounds. Well, each medical kit weighs 10 pounds, and so I can say that's 10x, and each container of water, that whole kit is going to weigh 20 pounds. So 10x plus 20y, only working in pounds, has to be less than or equal to 80,000. We can simplify this a little bit. If we divide everything by 10, we could say, well, this is really x plus 2y is less than equal to 8,000, just to make it a little bit simpler. All right, next thing we want to look at is, well, how much space is this taking up? So a total volume of 6,000 cubic feet. And again, that is the max. So I want my value, my function that I create to be less than or equal to that. Well, each medical kit is only 1 cubic foot, and each container of water is also 1 cubic foot. So I could say 1x plus 1y is less than or equal to 6,000, or I could just say x plus y is less than or equal to 6,000. All right, and so my constraints on here, I have multiple constraints that I'm working with. This is a constraint, this is a constraint, this is a constraint, and this is a constraint. Also, I want to figure out what the objective function is. So the objective function comes from here. How many of each to be set in order to maximize the number of victims aided? And then what is this maximum number of victims that we're working with? So I could say victims served is going to be equal to 6x, because each medical kit will aid 6 people, and then each water kit will serve 10 people. So victim served 6x plus 10y. That is our objective function. This is ultimately what we're going to work with, that we will get this maximum amount. But we need to identify what x is and what y is going to be. So how many medical kits and how many containers, kits of this bottled water that we're working with. So 6x plus 10y is our objective function. We're not going to graph the objective function. The graph, we're going to use our constraints in these green boxes and then identify vertices from there. All right, so just rewriting this again. So if I were to graph the feasible region, so again, x was greater than or equal to 0, y was greater than or equal to 0. I also had x plus y is less than or equal to 6,000. If I wanted to graph this, I can do it right here from standard form. If I said my x was 0, then y would be 6,000. So if I'm up here at 6,000, that's going to be a point. If I set y equal to 0, then x has to be 6,000. So that's down here at 6,000. I could graph this line. It's going to be a solid line because it was less than or equal to. If I wanted to graph the other function, which we said was x plus 2y, is less than or equal to 8,000. Again, I can graph this in standard form. If I set x as 0, then 2y equals 8,000. 8,000 divided by 2 gives me 4,000. And so my y value when x is 0 is going to be here at 4,000. And then if y is 0, x is going to be here at 8,000. This was my inequality. And so I'm going to have just a solid line here. X greater than 0, y greater than 0. If I were to do some shading now, so x has to be greater than 0, so I know I'm going to go this way. Y has to be greater than 0, I'm going to go this way. My first equation here, y is going to be less than 6,000, so thinking vertically, I'm going to shade down. So this one is going to be shaded down. This one here, second one, 2y less than or equal to 8,000. So again, I'm not going to have any negatives where I have to reverse the sign. So y has to be less than my line. So this one's going to be shaded down as well. So this right here is the feasible region. And then from there, I can figure out what some vertices are. So our vertices are going to be here, 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 and here. So I'm only looking at the vertices for my feasible region. Step 3, identify all of those vertices. So this one was easy. This was 0, 0. This one was 6,000, comma, 0. This one we don't know. We can solve for that one here in a minute. This one is at 0 and 4,000. So to solve for this value right here, again, our two inequalities were x plus y is less than or equal to 6,000, and then x plus 2y is less than or equal to 8,000. To solve these, I just need one to be an opposite. So I'm going to rewrite this, and we can just write it as equations because we're trying to solve. So x plus y, I'll say, is equal to 6,000. I want to add to eliminate, so I'm going to multiply this by negative 1. So this now becomes negative x minus 2y is equal to a negative 8,000. Add to eliminate of a negative y is going to be equal to a negative 2,000. If I divide by negative 1, divide by negative 1, I'll say y equals 2,000. So I know the y coordinate of this is 2,000. To find that x coordinate, I can just substitute back into any of them. I'll choose this top one here. So x plus 2,000 equals 6,000. So if I subtract 2,000 from each side, x equals 4,000. So this coordinate is 4,000, 2,000. So that's our vertice where those two lines cross. Now the next step is to find the value of the objective function at every single vertex point. So again, we had all those points we were working with. So I'm just going to make a quick little t-chart. And then our objective function, remember, was victim served is going to be 6x plus 10y. So we have to test every single vertex point in that function. So we had a vertex of 0, 0, 0, 4,000, 4,000, 2,000 was that one we found where the lines crossed, and then 6,000, 0. So plug all of those in. So 6 times 0 plus 10 times 0 equals 0. And again, we're trying to maximize. We're trying to find the biggest number. 6 times 0 plus 10 times 4,000 is going to be equal to 40,000. 6 times 4,000 plus 10 times 2,000 is 44,000. And then 6 times 6,000 plus 10 times 0 is 36,000. So again, we are trying to maximize. I can see here, looking at when I put these points in here, this was the maximum value. So the maximum value, the maximum number of victims served is going to be 44,000 victims. So step 5, what is the vertex producing the optimum value of the function? Well, we found that was at our 4,000, comma, 2,000. And again, X is representing our medical kits. So 4,000 medical kits, 2,000 bottled water. And when I do all that, it ends up being 44,000 victims served. Okay, so what is the vertex producing the optimum value of the function? So here in green, how many of each should be sent? Well, that's 4,000 and 2,000. What is the maximum number of victims served? I got a 44,000 victims served. So these are pretty long problems, but just take it step by step, identify that key information, and then you'll eventually get to the correct answer. Let's do another one. I'm just going to set this one up for you just so you have an idea. We can also look at minimizing costs. So this one says Alex takes multivitamins each day. She wants at least 16 units of vitamin A, 5 units of vitamin B, 20 units of vitamin C. Capsules cost 10 cents each and contain 8 units of A, 1 of B, 2 of C. Chewable tablets cost 20 cents each and contain 2 units of A, 1 of B, 7 of C. How many of each should she take to minimize her cost yet fulfill her daily requirements? Again, this idea of each. What items are we working with? Well, the items that we're working with are capsules and chewable tablets. So if I say that X is representative of the capsules and Y is representative of chewable tablets. So that's that each piece that I'm working with. All right, so now I can create some constraints from this. All right, so it's going to be A, B, and C. She wants at least 16 units of vitamin A. So if I thought of that, my 16 units of vitamin A, at least. So I want my function to be bigger or equal to 16. All right. And now I'm thinking, okay, for 16, that's vitamin A. So I'm going to work with 8 units of vitamin A for my capsules. So I would say this is 8x plus chewable tablets are 2 units of A. So this would be plus 2y. She wants 5 units of vitamin B. And again, it's at least 5 units of vitamin B. So this would be 5. I want my function to be greater than or equal because 5 is going to be the minimum. Capsules, 1 of B. Tablets, 1 of B. So this would just be X plus Y. And then at least 20 units of C. So this would be 20. And then for each one, 2. So capsules have 2 of C. So this was 2X. And then 7 of C. So plus 7Y. So those are my constraints. I'm only working, so X is capsules, Y are chewable tablets. X has to be positive, Y also has to be positive. I can't have any negative values. So those are the constraints on this one. If I wanted to look for the objective function, it says how many of each should she take each day to minimize her cost? So I know my answer is going to be cost and yet fulfill her daily requirement. So cost is money. So I know capsules are 10 cents each. Okay, so I can rewrite this as 0.10x plus I have 20 cents each for the chewable tablets. So plus 0.20y. So that's going to represent my cost objective function, which I ultimately would work with. So the hardest part on these is pulling out the necessary information, creating your constraints, creating your objective function. Once you have the constraints, you can graph that, identify the vertices, test all of those vertices in your objective function. This one was a minimized one, so we're going to look for the smallest number, and then that will be our solution. So 5.6 part 2 is in Math Excel, due Sunday 4/19. Again, email me, contact me if you have questions on any of these. I'm more than happy to make a video to send over to you. We can do a one-on-one video chat, or it might be something that I can just answer via written response in email, Schoology, wherever you prefer.